All right, welcome to my talk, Making oRAT Go. So today we're going to be looking at analyzing a very interesting piece of Mac malware. But the way we're going to do this is slightly different. Essentially, we're going to create a custom command and control server, and then basically ask the malware the right questions so that it reveals its capabilities to us. So we're going to start with some background information. We're going to talk about the configuration and the protocol of the malware. As I mentioned then, we're going to talk about how to create a custom command and control server and ultimately reveal the capabilities that way. So first, some background information on this threat. Earlier this year, researchers at Trend Micro uncovered a new APT group. And the interesting thing to me about this APT group was that they had macOS capabilities, specifically a new Mac malware called oRAT. Now, Trend Micro and SentinelOne did some analysis of this malware sample, but it was largely a triage. So yes, they identified the infection vector, they talked about the configuration information, and did mention some likely capabilities. As we can see by the quote on the slide, they ran into some difficulties getting the malware running, so a lot of their analysis was somewhat high level, based on static analysis. I prefer dynamic analysis because ultimately you can confer the capabilities. So what we're going to do is we're going to build upon their analysis to comprehensively confirm their findings and get to the bottom of this. Now, as I mentioned in the introduction, our approach is kind of different. Many of you have probably done malware analysis, but not via this approach. I like this approach. It's a little more interesting, and I believe it's ultimately more efficient. So the general idea is as follows. We're basically going to get the malware to connect out to a command and control server we control. We're then going to task the malware, give it commands to execute. On the system where the malware is running, the victim, the infected host, we're also going to run various monitoring tools, process monitors, file monitors, network monitors, to observe how the malware responds to our tasking. If we task it correctly, we'll be able to see exactly what it does, and also then it should respond to our custom command and control server with its results, allowing us again to comprehensively understand the capabilities of the malware without actually having to do a ton of reverse engineering. Now, obviously, there are some prerequisites for these. There's three specific ones. First, we have to figure out a way to reconfigure the malware or get it to talk to our command and control server instead of, obviously, the attacker's one. Second, we have to at least understand the protocol of the malware so that when it does connect to our command and control server, we can ask it the right questions to coerce it to perform its actions on our behalf, revealing its capabilities. And third, as I mentioned, we are going to need monitoring tools so we can observe the malware in action. But good news, we can use Objective-C's command line utilities to perform this. Now, anytime I get a new Mac malware sample, I like to perform some basic triage. This is going to be similar to what Kristen talked about. So before we go into diving too deeply in the malware, let's do some basic triage. We want to figure out things like its file type, code signing information, and also run the strings utility to see if anything interesting pops out. Running the file command, we can see it's a mock-o binary. This is important to know because a lot of static and dynamic analysis tools are file type specific. If this malware was a compiled Python script, we would end up using different analysis tools. In terms of the strings, there's really not too much, except for the fact that the malware does appear to be packed by UPX. When an item is packed, the UPX strings are added into its strings. And finally, using what's your sign, we can see that this item is unsigned. So TLDR, we have a packed 64-bit mock-o binary. Now, anytime you have a malware sample that's packed, you're going to want to unpack it first, because what packers are essentially obfuscators or encryptors that take all the binary, compress and encrypt it, thwarting static and often dynamic analysis. So step one, you want to unpack the sample. Luckily, binaries that are packed with UPX are trivial to unpack. You just rerun the UPX binary with the -d flag, give it the path to the item you want to unpack, and it will be unpacked. Interestingly, we can see on the slide that the item unpacks to almost 10 megabytes. That's huge. Now that the item is packed, we can do some more triage. One of the things I like to do is look at dependencies. This is something Kristen talked about as well. This often can tell you what dynamic libraries the malware is going to leverage or utilize. For example, if it's linked against the AV Foundation framework, it's likely going to abuse the user's webcam or microphone. Well, if we run dependencies, extract the dependencies from oRAT, we can see there's really not that much. That's pretty strange. But if we run the strings command again, now that it's unpacked, we can see what appear to be a large number of static dependencies. Static dependencies are third-party libraries that have been statically compiled into the binary. This is one of the reasons the binary is so large. And based on those strings, we can get some sense of what the malware might do. For example, we see dependencies related to networking, daemonization, and cryptography. Also, looking at the paths from the dependencies, it looks like maybe some of these are written in the Go programming language. So now we're going to do a brief tangent. We're going to talk about reverse engineering binaries that are written in Go. In Lexi and Lucha's presentation, they mentioned some of Wizard updates components were written in Go as well. So this is kind of a trend we're seeing. And it's important to talk about this because there are some nuances or challenges when reverse engineering binaries that were written in Go. Good news is there's some great resources. So if you're new to reverse engineering Go, which I was, I found these very useful. So first off, you might be wondering, how do we know that a binary is compiled from Go source code? Turns out it's pretty easy. There's going to be a Go build ID embedded in the binary. So if you run the strings command, once it's been unpacked, you will see that. Also, if you throw the binary in a disassembler or decompiler, you will see that near its entry point, it calls into various Go runtime bootstrap functions. Now, I mentioned there's some challenges, some nuances that come about reverse engineering a binary that was written in Go. The first is really just the size. Go binaries are massive because a lot of the libraries are statically compiled in. So the challenge we have, therefore, is to really ignore the statically compiled third-party libraries. They're often open source and don't do anything malicious, but instead find the malicious code that we want to focus in on. And we can see this, how the size is impacted, by creating a simple hello world Go binary. And if we can compile that, we can see that's over 1 meg, which is huge for a simple program that prints out 1 line of code. But again, this is because of all the static Go libraries that get compiled in. Another challenge that comes about when reverse engineering binaries that are written in Go is the fact that Go strings are not null terminated. And a lot of reverse engineering tools struggle with that. So for example, I use Hopper. You can see if we load the hello world binary into Hopper that it struggles with the strings. So we can see it's identified a printf function, but it doesn't know what string is being printed out. This is kind of problematic because it's really nice to see strings inlined in the disassembly to figure out what a sample is doing. Now, if we manually follow that cross-reference, indeed, we can see the string. So again, just something to be aware of. Now, one of the brief tangent, and this is also similar to what Kristen talked about yesterday, is I briefly want to mention how we virtualize an environment to do malware analysis on macOS. As Kristen mentioned, Parallels is really the way to go. I equally struggled with VMware, so I do have struggles as well. And I actually originally went out and bought a refurbished Mac M1 so I could do malware analysis because the virtualization software just sucked. But then I said, okay, now Parallels is great, right? You download it, you install it, there's a pre-built macOS M1, and the end result is you can now virtualize macOS ARM on an M1 system. This is great. I did notice, though, that when I installed it, that it popped up asking for permissions. This is really unsurprising. Essentially, every installer is going to ask for permissions so that it can perform certain privileged actions. If you know me, though, I really like looking at installers because people often get it wrong. So I decided to take a quick peek at what Parallels was using, and I noticed something interesting. So behind the scenes, when you double-click on the installer application, it downloads a second disk image from the internet, which is the latest version of Parallels, and then this is what gets installed. So if we run a process monitor, we can see that once the user has authenticated, various binaries are now executed with root privileges. This makes sense. The installer needs to have certain privileges to perform its actions. Unfortunately, or interestingly, these binaries are owned by the user, which means we might be able to tamper with them. But unfortunately, it's written or executed from a read-only disk image, so this appears safe. Right? No, not at all. So here's a 0-day that affects the latest version of Parallels. So if you're using Parallels, like myself, be careful. And basically, we can exploit this vulnerability to elevate privileges in 5 simple steps. And this could be abused by a local adversary that wants to elevate their privileges, or by malware that's already on the system that equally wants to gain root. So the first thing it needs to do is it needs to detect the installer mounting that second disk image. Then what it's going to do, it's going to send a sig stop command to the installer to pause the installer. Say, hey, wait, hold on, don't do anything yet. It then goes and remounts that disk image with read-write permissions. It then infects the binaries on that disk image and then tells the installer, OK, continue on. End result, you get a root shell. So I wrote a proof of concept for this last night after the party. It might not work, but I did pray to the demo gods. So what we're going to do here is we're going to start the exploit, and you can see it's waiting for the installer to be run. We're then going to double-click and run the installer. We're going to make sure not to participate in the experience because, I don't know. And we'll see that it found the PID of the process installer. And as the item downloads the disk image, as soon as the installer image goes to mount that, we are going to pause the installer, quickly remount the disk image, although we don't have to rush because, in theory, we're off and running. The installer then is just going to continue on using the disk image. At this point, we haven't tampered anything. We've just remounted the disk image as rewrite. Now, there's a password prompt from the installer. At this point, behind the scenes, we're going to infect the disk image. And then when the user goes ahead and completes the install, you see we get a root shell. And actually, we get another root shell. Hooray. The installer is going to keep going and going to keep giving us lots and lots of root shells. So we're just raining root shells. The installer is going to complete. It's going to launch the VM, none the wiser. Wait for some animations. Next. OK, back to the malware, because this is a talk about malware, right? It's not about 0 days. So recall that our goal is to coerce this malware to talk to a custom command and control server so that we can task it to uncover its capabilities. First step, though, as I mentioned, we need to find a way to get the malware to connect out to us. So let's talk about how to reconfigure the malware so it connects to our command and control server. Trend Micro touched on this and talked about the fact that embedded within the malware is encrypted configuration information that contains information, for example, about the command and control server. We can confirm this if we look at the end of the malware's binary. We find an encrypted blob followed by an AES decryption key and a size. One point to note, when you unpack the binary, even if you tell UPX to respect the overlay, the data at the end, it does not. This took me a while to figure out. I unpacked the malware, and the configuration information did not exist in the unpacked sample. So now we have the encrypted configuration blob. We have an encryption key and a size, so it's pretty easy for us to write a decryptor. So be nice. This was my first program I've ever written in Go, but it is a decryptor for the oRAT's configuration information. Super straightforward. So it opens the malware, grabs that encrypted configuration file, and then decrypts it via AES in GCM mode. It's very straightforward. When we execute it, we can see we have the decrypted config. So let's look closer at that decrypted config. At the top, we can see there's some information to set up the malware to run in gateway mode. We don't really care about that. But in the middle, we can see, yes, indeed, there is command and control information, specifically the address and port of where the malware will connect out to, and then also the protocol. Trend Micro documented this as well. Basically, there's 3 different types, TCP in plaintext, or encrypted and/or encrypted UDP as well. So now let's reconfigure the malware. We can see we have a new config that contains now the address of my command and control server. I then wrote a second program, my second Go program, making great progress here, to re-encrypt the configuration and put it in at the end of the malware's file. This is basically the opposite because AES is symmetric. So again, pretty straightforward. We're just encrypting that configuration. We can confirm that that indeed works. We do a hex dump of the malware, and we can see that at the end there's our now encrypted configuration. And more importantly, if we set up a netcat listener on the address and port we specified, run the malware in parallels, we get root, yes, but also then the malware will connect out to our command and control server. Now, I continued to do a little bit more triage, looked at the disassembly of the malware, and I found out that you could non-persistently configure it as well in another method. So it turns out the malware looks for various RK_environment variables, and if those are set, it uses the values from that instead of from its encrypted configuration. So I've documented them on the slide. You can see there's 3 separate ones. There's RKNet, which allows you to specify the protocol. RKadder is the address of the command and control server. And then RKdebug puts the malware in debug mode, which means various debugging strings will be printed out, and also that the malware will not daemonize. This is great. It makes debugging the malware a lot easier. So here's an example of that. We set these various environment variables in a terminal, execute the malware in a debugger, and we can see when it goes to execute some of its logic, indeed, it is reading the values from that. So this is helpful. This just allows us to reconfigure the malware on the fly from a command line. But again, we also can use the more persistent mechanism, reconfiguring and re-encrypting the config. All right, so step 1, check. The malware is now talking to our custom command and control server. Now, we want to talk back so we can coerce the malware to reveal its capabilities. So we have to understand the protocol that the malware expects to speak. So if you noticed a few slides back when the malware connected out, the traffic did look like standard HTTP, but at the beginning there was a question mark. This is Netcat saying, hey, I got some binary data. It's not printable. I don't know what it is, so I'm just going to put a question mark. So there's something slightly strange going on. So I dug into the malware a little more and noticed it was statically linked against and utilized against this library called smux. We have the path, and it turns out it's an open source project, so we can go on GitHub and read the README file. And as we can see on the slide, it is a multiplexing library for Golang. So what is multiplexing? Well, the idea, and this is actually pretty slick from the malware author's point of view, is that multiple streams of data will be multiplexed over one connection, for example, to a command and control server. So in the middle of the slide, we can see there is one connection from the infected system to our custom command and control server. We'll see, though, there's multiple flows that are all multiplexed into that one connection. So at the end of the day, the malware is only ever just going to have one connection out to a command and control server, but that one connection is going to contain various multiplex streams, for example, command and control tasking, a heartbeat, et cetera, et cetera. Now, this is great from the malware author's point of view. It's a lot more efficient, right? You're not generating a new connection each time you want to send some traffic. You just utilize the one existing one. And also, it's somewhat stealthy. However, this means we are going to have to write a command and control server that is equally multiplexed, because when we get data from the malware, this is going to come in on a multiplex channel. So we're going to have to demultiplex or demux it in order to extract each of the streams and the information that the malware is sending to us. Well, we can also use that smux package, right? It's designed for both clients and servers. So what we're going to now do is write a command and control server that uses the smux package so that it can talk to the malware because everything now will be multiplexed. So again, I know nothing about Go. I was like, how do you even install a Go package? So go on Google. Turns out you type go install. And this will then download and install the Go package. And then within your code, you just specify an import. And that library is ready to go. So step 2, then, we have to listen and accept for connections. This doesn't have anything yet to do with multiplexing. This is just in Go, how you open a listening socket and accept connections. When we compile and run this, we can see that the malware indeed connects out. We're already doing that via Netcat, so no real progress yet. But now we get into the core of the command and control server, where now we start utilizing some of the smux libraries, APIs, and functions. So first thing we do is we initialize a mux server. We then accept a mux stream, and then we handle the stream. And we can see now when we print it out, we are starting to parse the malware's responses fully. So now the malware is talking to us. We kind of understand the fact that we have to multiplex and demultiplex traffic. But how do we ask the malware to perform its actions, right? We need to figure out how to task that. Well, Trend Micro also touched on this, and they basically said that what happens is the malware starts a local server on the infected system that actually listens for URL requests from the server and then will act on those. And the parlance in Go terminology, or I guess in web stack technology, I don't understand any of that, is this idea of routers. And routers basically map requests to actions. So a client can make like a GET request to some API endpoint. The router for that will then take that request, extract the API endpoint, and say, OK, you're requesting ABC. I will execute now the method or the code for the ABC API endpoint. So here's kind of an example over that, a conceptual overview. When the request comes from the server, the command and control server, the malware also has a local server listening for these requests. It's going to look up the handler for that request and execute that. So we can look a little closer at this if we reverse engineer the malware, specifically its register route method, and we can see that it does a few things. It first specifies a route handler. This is the API endpoint, the tasking request. Then specifies the route request verb. This can be get or post. Specifies the route request, and then ultimately registers this. In a debugger, we can confirm this in action. And the point of the slide is just to show that now from the command and control server, when we make the appropriate request, the malware locally will access that request, look up the correct handler for that, and invoke that. So it's just kind of a slick way to do tasking processing. We can continue to reverse that register router function to extract all the commands, the routes, the requests we can make to the malware. And we can see that they're all pretty verbose and fairly descriptive. So here's a table and the verbs, and we will see some of them in action. Some of these understandably take parameters, so if we do a little bit more reverse engineering, it's trivial to figure out. So for example, for the port scan command, we can see that it takes a host and a port. So now we have the ability to task the malware. Maybe. Or do we? So we understand the protocol and all the components, but it really took me a while to actually get the request to the malware, and we'll see why in a minute. So if we debug the malware, we can see that it calls the start server method, and this is the standard echo server. So I said, OK, well, there probably should be a listening socket, something that maybe I can connect to send the tasking from the command and control server. But there's no listening sockets, so I was perplexed. Well, the answer, of course, goes back to the fact that the malware multiplexes everything. So even though it starts up a local server to listen for tasking, that's not going to generate a new listening socket or a new connection. That instead is going to be tied to the existing multiplexed session or streams, and then tasking has to come over that. So this is how we can ultimately task the malware from our command and control server in 3 easy steps. So step 1, we open a new stream based on the existing multiplex session. So the session is the one connection. We say, hey, we want a new stream because we're going to send some data over that session. We then task the malware by writing our request to that new stream. It'll get multiplexed and sent to the malware. The malware will then demultiplex that and handle it to pass it to the appropriate router. And then finally, we can also read from that stream to get any responses. Now, this looks simple, and it is. It took me like a week to figure out, embarrassingly. But end result, we can now task the malware. So we know the commands the malware expects. We have the ability to task it. The goal is now to task the malware to observe it in action to, for example, confirm its activities and its capabilities. So start with some simple ones. The first one we can execute is the info command. We send a GET request to /agent/info. Again, the malware is going to check in. We open a new stream. We send this request over the MUX connection, and the malware will handle that. As a response, it sends us back a 200 OK, saying, hey, I got that. That was a valid request. I handled that. And then its response, as we can see, is a complete survey of the infected system. So again, we didn't have to reverse engineer the info logic to see what type of survey it was, or even the fact that it was a survey. Malware kindly showed us that by returning survey information. We can also exfiltrate files via the download command. Again, the malware is kind of set up a local server, so its idea of downloading it is sending a file up to our server. This takes 2 parameters, one parameter, a file path. And you can see when we execute this command, if we have a file monitor running on the infected system, that we can observe the malware, as expected, opening the file, reading its contents, and then exfiltrating it back to our command and control server. I was also interested in the fact that the malware appeared to support screen capture capabilities. There's a variety of ways to do this on macOS, so I was interested in how it implemented it. Unfortunately, when I tasked it, it said, sorry, not available on macOS. Bummer. Other abilities, though, we can set up an interactive tunnel. This is kind of a neat capability for the malware to have. So what we can do is we can make the agent net request. This takes various parameters like a host and a port of the endpoint of the tunnel. Once that's set up, the malware comes back and says, OK, you are now connected. Now anything we send from the server will get multiplexed over to the malware. The malware will demultiplex that and send it off to the tunnel. The endpoint, which we can see is just a simple netcat listener on this slide, anything we type or add to that tunnel will be routed back to the server. So in this case, the malware has now basically become a tunnel or almost like a proxy server. We can also do a port scan. Again, I was interested in figuring out how this was implemented. Turns out pretty basic. So we make the port scan request via a GET request. Again, that gets multiplexed over to the malware. It does a port scan. If we're running something like Wireshark, we can see it just simply tries to connect to each of the ports in the range you specify on the specified host. And any that are open, the malware will observe that and then respond that back to our command and control server. And then finally, the kill self, unsurprisingly, is how the malware can self-delete. So this was the last command I ran. And we can see that via a file and process monitor, the malware will fully self-delete. In the file monitor, we can see the malware, once it receives this command, will unlink or remove itself. And then in the process monitor, we can see that the malware's process will exit. And of course, on the server side, on our command and control server, the socket connection will be closed, and we get an error message saying that the client has disconnected. OK, so let's wrap this all up. 3 takeaways. First, I think it's really important to study APT Group's malware, because this gives us really good insight into the capabilities, the approaches, the sophistication, or lack thereof, of advanced or at least persistent adversaries. Also, hopefully, I've illustrated the fact that analyzing malware via custom command and control server can be a pretty efficient approach that allows us to comprehensively analyze a malware sample. Right? So we had to do some initial research on the configuration and the protocol and the tasking. But once we had that, we could simply ask the malware to perform actions, and then via our file monitors, process monitors, and network monitors, see exactly what it was doing. Also coupled with the fact that it kindly sent us back results to our command and control server. And thirdly, I think this is pretty cool, we now have a reconfigurable malware and a compatible command and control server. So imagine this was written by the Russians, the Chinese. If I'm the Americans, I'm taking this and deploying this on targets that might be compromised. And then if that was ever to be found out, I'm not going to get blamed. The original malware authors will. So using this capability also has offensive options, I would say, that really provide a high level of plausible deniability. So that is a wrap. I think we have a few minutes for questions. Again, thank you so much for attending this talk. Sharvo. Yes.
Do you know what kind of debug input printed, and did it give any more insight into malware?
Sure. So the question was, the malware supports or looks for custom environment variables. And one of those was RK_debugged. And if that was set, 2 things happened, right? It printed out more debugging information. I'll get to that in a second. And also, it prevented the malware from daemonizing itself, which made it way easier to debug. So the debug strings weren't super helpful, but it did print out some more error messages. For example, if it couldn't connect out to the command and control server, it would print out that fact. So it was definitely helpful. And I think it's good anytime you are analyzing malware if it has debugging capabilities built in, which a lot does. Malware, I always say, is simply software with malicious purposes. And so malware authors are software developers, so they're going to put in debug logic and debug code. So if you find malware that has debugging logic compiled in, if you can find a way to trigger that to be activated, in this case it was pretty easy, it does make your analysis a lot easier. Anytime it's spitting out debug strings. And so when I did find that, that did facilitate my initial triage and help me kind of build a compatible command and control server that I could task. Great question. Any others? Yes?
So this malware was kind of more sophisticated than what we've seen on the macOS one. This kind of multiplexed connections
Yeah.
more stealthy. Do you think the future would be like they'll set up a WireGuard tunnel with a RFP that you won't have access to and kind of make it even harder?
Yeah, great question. So the question was, some of the multiplexing, it's a decently complex feature or, something that's decently sophisticated. At least shows that it was written by a real software engineer. Like, I would never write that, right? And so the question was, do we expect more advancements? Because there's definitely next steps. And I would say yes. I mean, I've spent a lot of time looking at Mac malware, and 5 years ago, it was mostly pretty boring stuff. Now we're seeing adversaries utilize zero-day exploits. The talk earlier from the Google researchers, I mean, that was a pretty sophisticated sample. Well, there's really a lot of tips that the malware authors are leaning into, so I would expect them to see that, and the malware continue to evolve. This is interesting because I think if a real software engineer would have looked at this very quickly, they would be like, yeah, this is how you write a Go program, and of course you multiplex connections. And then very quickly would have been able to write a compatible command and control server versus, me taking a week. So again, I think there's something to be said by understanding how software is written, because when you are reverse engineering malware, it's essentially doing the opposite of that. Yes? Yeah, that's a great question. So the question was, Patrick, why are you dropping 0 days? Which is totally a valid question. For me, I start with, is this going to impact everyday users across the board? And so if it's a local vulnerability, I'm essentially like, no. Because for better or worse, I always judge bugs based on the quality or based on the question, would a three-letter agency like the NSA, where I used to work at, would they use this bug? Would this bug be useful to them? And if the answer to that is yes, it's like, okay, I'm going to go to the vendor and make sure it's fixed. Is the NSA going to use a bug to elevate privileges in parallels? Like, no. Also, the number of users using parallels is very small, and malware would already have to be on the system to elevate that. It's way easier to use, in my opinion, a vulnerability that affects macOS core that would work on every system that could be triggered immediately. So to me, a bug like this, while illustrative, I don't think it has widespread impact. So I don't think it's going to be putting a lot of people at risk. The DEF CON Zoom bug, a little different because that impacted a lot more users. The main issue with that is I had reported bugs to Zoom 8-9 months ago, and it literally took them 3/4 of a year to fix. Those bugs were trivial to find, and again, given my background, I always assume that if I can find a bug, other bugs, that same bug could be found by other adversaries or attackers as well. So, it really comes down to each bug is different, but I generally try to answer the question, what is the impact, and also, how is the company responsive to that? Parallels doesn't have a bug bounty program. Not that I'm looking for a payout, but that to me is a sign of a mature security. So, hopefully they'll fix it soon. But again, that's a great question. The fact that I'm not beholden to some large company means I can also get on stage and pull shenanigans like this with not a lot of repercussions. For better or worse, here we are. I mean, I just really wanted to spice up the malware talk. I love talking about malware, but I'm like, I'm getting a little older. I got to keep finding 0 days. I don't want to lose my technical acumen, et cetera, et cetera. But totally valid question. I appreciate that. Any more? Yes, in the back. Adam. Great question. So the question was the size of the binary, the fact that it was 10 megs. What was the reason? And I had a slide with a quote from Jags that basically said, hey, Go binaries are massive because of the fact that all the libraries are statically compiled in. And that was exactly the reason for this as well. So the malicious logic itself wasn't incredibly large. It was just a 64-bit Intel binary, so it wasn't a FAT or universal binary. So in this scenario, and this is true with most Go binaries, the size is simply based on the fact that many of the Go runtime and other third-party libraries are statically compiled in. So you're going to just have massive executables. But again, the good news is you can ignore the majority of that because it's like third-party libraries. But there are some challenges to finding, hey, where's the core malicious code? And some of the resources I talked about on the slides dig into how to do that more. Great question. Any other questions? Awesome. Well, again, thank you so much for attending my talk.